Well, let's talk a little bit more about what it takes to be a qubit. So this week we've been looking at the DiVincenzo criteria and ideas surrounding the physical properties of qubits related to their coherence. And we kind of visited the main 5 criteria: a scalable physical system with well-characterized qubits, the ability to initialize the state of the qubits, long relevant decoherence times, the concepts of T1, T2, and T2 star, the universal set of quantum gates, qubit-specific measurement capability, and then the 6th and 7th of the DiVincenzo criteria relate to quantum communication and the ability to couple traditional qubits to photons so that you can move quantum information over distance. Then we also talked about some fun examples of coherence, the cat, and we'll mention quantum erasers. So I thought it would be fun to start with DiVincenzo's look back on the DiVincenzo criteria, which he never called them that, obviously. And so in his retrospective, you can see him here in 1994 at this Villa Gualino meeting. And he said that this is sort of where the idea for the criteria sort of came up. So just before this photo was taken, he was watching a talk by Ignacio Ignacio Sirac and Zoller, where is Zoller? There he is, Peter Zoller, about their idea for doing quantum computation with trapped ions. And it was just an idea at the time, and it was kind of presented as a proposal in response to ideas about developing quantum algorithms that were introduced by this guy, Arthur Eckert, earlier that year at another conference. And what David DiVincenzo sort of realized is that maybe these ideas that they were putting forward about trapped ions could be applied more generally to other types of quantum systems. And that's where sort of the first kind of idea for his criteria kind of came about. One thing that I think is really cool about this story is that it really kind of harkens back to a different time of doing science, even though it was only 1994. Big ideas in an emerging, very new field were kind of propagated and developed at small conferences like this one. And I think that's pretty cool. It's something that still exists in the form of like ordinary research conferences and certain types of specialized conferences today, but not like it did in the past, I think. And so DiVincenzo said that when he started writing down the criteria, he was, over the next few years, he was kind of paying attention to the other things that were happening in the field. And the first thing he started to notice was that lots of people were writing sort of papers that had one-off experiments that were basically paying lip service to the glory of quantum computing. And they presented, some tiniest part of the picture. And he said he wanted to write the criteria for those kinds of people because he wanted to shake them up and maybe even scare them off. Don't pretend that your impressive little experiment is actually a big step towards the physical realization of a quantum computer, exclamation point. That's what he says in the article, which I think is pretty blunt. And then the second thing that he was paying attention to was the advent of NMR quantum computing, which he thought was a lot more like on the nose, a lot more close to what he thought quantum computing would eventually look like. But he had pretty big feelings about the scalability and the ability to do real quantum computing in an NMR because the systems are highly mixed states. And so some of his criteria and discussion kind of hints at his bias against NMR quantum computing, even though he thought it was a pretty great development. Yeah. So these criteria have been labeled promise criteria, and that name of promise criteria came about in the 2001 QISE roadmap from the government. And this is kind of where they became labeled as the DiVincenzo criteria. And when DiVincenzo was kind of reflecting back on, where we're at today or a few years ago with his criteria, he points out that a lot of people had said that they've all been met. So all of the main 5 have been accomplished. And so, but we still don't have a scalable quantum computer. So he asks the question, was I wrong? Did I fail? And he kind of points out that this kind of idea that these are promise criteria, that these are going to bring us to some highly promising situation for going further towards building a quantum computer. And they basically only get us the components that would work the way they need to for this to happen, but actually building a quantum computer is a much bigger task than just fulfilling his 5 criteria. Thoughts or questions about how he kind of came about with these ideas? So one of the things he points out at the end of his little reflection is that there's been a few other people that have kind of created little roadmaps to the future of quantum computing. And he points out this really beautiful science paper from DeVicenzo and Sholkoff. So whoever's doing superconducting qubits, if you haven't read this article, it is great and you should read it. But in the beginning of this article, they talk very much more generally about at the systems level, what needs to happen to get to quantum computers. And DiVincenzo calls these the complexity steps. And so in this paper, they kind of lay out this 6-7 step kind of sequence that needs to happen to get there. And the first step is that we need a quantum system to be controlled sufficiently to hold 1 bit of quantum information long enough for it to be written, manipulated, and read. And so that's kind of step 1, and that's definitely been achieved today. And then step 2, or stage 2, is that small quantum algorithms can be performed. And that's definitely been achieved today. And it's these 2 steps for which you do need all 5 of the DiVincenzo criteria to be fulfilled for this to happen. So this is kind of what DiVincenzo has brought us to. So then what DeVicenzo and Sholkoff say is that, okay, so the next stages of developing towards a quantum computer involve things that are more complex and introduce requirements related to quantum error correction. So basically everything here on requires some level of quantum error correction. So in the 3rd stage, they envision that some errors could be corrected by so-called quantum non-demolition readout or error syndromes like parity. And this idea of a non-demolition measurement means that the uncertainty of the measured observable doesn't increase from its measured value during the subsequent evolution of the system. This is kind of the most classical type of a measurement. It's the least disturbing or least perturbing type of measurement in quantum mechanics. And this stage of quantum computing development has been achieved by trapped ions, by neutral atoms, by superconducting qubits, and probably by solid-state qubits by this point. So those 3 stages are fulfilled. Stage 4 is all about realizing quantum memory, where quantum error correction leads to a coherence time that's longer than any of the individual components. And that goal has not yet been fulfilled. So that's sort of where the leap needs to come. And the final two stages in reaching the ultimate goal of a fault-tolerant quantum computer require the ability to do all single qubit operations on one logical qubit, which is basically an effective qubit protected by active error correction. That's what they're calling logical qubits, practical logical qubits. And the ability to perform gate operations between many logical qubits. So we're kind of stuck here. So we'll see what happens in the next several years. But the DiVincenzo criteria are sort of the starting point, and then to actually build the systems is the kind of current challenge. Realizing quantum memory, where quantum error correction leads to a coherence time that's longer than any of the individual components. And that goal has not yet been fulfilled. So that's sort of where the leap needs to come. And the final two stages in reaching the ultimate goal of a fault-tolerant quantum computer require the ability to do all single qubit operations on one logical qubit, which is basically an effective qubit protected by active error correction. That's what they're calling logical qubits, practical logical qubits. And the ability to perform gate operations between many logical qubits. So we're kind of stuck here. So we'll see what happens in the next several years. But the DiVincenzo criteria are sort of the starting point, and then to actually build the systems is the kind of current challenge. So let's go through some of the DiVincenzo criteria and think a little bit like more broadly about what these are saying from a practical lens. So the first requirement in the DiVincenzo criteria is a scalable physical system with well-characterized qubits. So that's sort of two things, right? Scalable physical system, well-characterized qubits. So we know that the permitted states of a single qubit fill up a two-dimensional complex vector space, and they can be written like A0 plus B1 and absolute value of alpha squared plus absolute value of beta squared equals 1. And as we'll see next week, when we put two of these qubits together, the sort of general state that we're going to get is A00 plus B01 plus C10 plus D11. So that's some kind of four-dimensional vector. And there's one dimension for each distinguishable state of this two qubit system. And these states are generically entangled. And in general, a collection of n qubits should be specified by a 2 to the n dimensional complex vector space. So when he says scalable physical system, this is kind of the thinking that he had in mind. I think that as materials people, many of us, we have something a little bit different in mind. So when you think about a scalable physical system, what do you think about? So we need a material platform, and we need an ability to manufacture qubits that are all identical to one another at some scale. Yeah, so this is a huge challenge, right? So this is where Neutral atoms and trapped ions win because they are identical. Calcium ion is always the same, no matter how you got it in your trap, it's always going to act the same way. Same with a neutral atom. When we go to something like an NV center, every NV center in a real diamond is going to look a little bit different. Exactly where that defect is in your material is going to affect its coherence properties. If it's near the surface versus in the core, how many of them there actually are in an individual, widget, diamond, is going to matter. So the solid state qubits, that's one of the biggest challenges, is the variation qubit to qubit. If you isolate the single two-level system, okay, that should behave well. It should behave identically, but it's really hard to do that. It's really hard to engineer a material that has one color center or one defect or one electron spin or whatever. All right, so what do we need to know about our qubits? So we need well-characterized qubits. Yeah, so what do you think he meant when he said we need well-characterized qubits? So what he meant is that we need to know the physical parameters of our system very accurately. We need to know the internal Hamiltonian of our system. And we need to know how those 0 and 1 states couple to other states nearby in the qubit. In the case of a calcium ion, for example, right, there are the two states that we're doing the measurement with, but there's lots of other states in that qubit, and we need to know how those interact so that we can isolate the two-level system we want to work with. And we need to know how our two states couple to the external world. So we need to know the Hamiltonian, that's like 1, and we need to know couplings to other states and to the external environment. So from a practical standpoint, if you think about the qubits that y'all are thinking about, what comes to mind for well-characterized? So if you translate this stuff to your favorite qubit, yeah, what do you think? Yeah, so knowing precisely that energy gap, that's a super big one. Because if you want to initialize and read out your qubit, you want to do manipulations, you need to very accurately be able to probe that gap or pump that gap. Yeah. And this is kind of getting us partially into the discussion of the measurement, qubit-specific measurement capability. So there is some overlap. So when we think about the practical qubits that are out there, so we need to know the internal Hamiltonian. We need to know what the 0 and 1 states are. So what are some of those 0 and 1 states for our qubits? So for trapped ions, for example, what is 0 and what is 1? What are our two states? Yeah, they're just just some pairs of energy levels in the ion. And that's true too for the neutral atoms. And these levels of an ion or an atom, they're held in linear electromagnetic traps. What about for photons? The polarization state, that's one possibility. There are, of course, others, but that's certainly a favorite. What about for spin qubits? Maybe that's redundant. Yeah. Little m sub s equals plus minus 1/2. What about for color centers? Yeah, ground and excited state. But it might not be the ground state that, the absolute ground state of the system. Yeah, it might not be the zero Fermat line, for example. What about superconductors? It's sort of quantized states of the superconducting state. So it's like Cooper pair charge or flux. Okay, so number 2 is the ability to initialize the state of the qubit into some simple starting state. And there's sort of 2 reasons that he highlights that this is necessary. What do you think are those 2 reasons? So number 1 is the kind of obvious thing. It's that if we're going to do a computation, we need a starting point. We need to know where we're starting. So if we're going to run an algorithm, you need to know where you're starting. And the second, anybody know what the second reason is? So it has to do with something we haven't talked about yet. So this idea of error correction. So to do error correction, it basically requires a continuous fresh supply of qubits in our low entropy state, in the ground state. And the need for this continuous supply of zeros, for example, rather than just an initial supply, is the thing that's giving everyone a headache. Yes, the conveyor belt. So the qubit conveyor belt. So we need a continuous supply of zeros. So if the time it takes to do the initialization of our qubit is relatively long compared to the gate operation time, then a quantum computer will have to be equipped with some kind of conveyor belt. You'll have to be able to move qubits away, initialize them over here, away from where the math is happening, and then bring them back. And that's super impractical. But that's kind of where we're at right now. So the 2 main ways that we initialize qubits are what? So the first main way is just to let them naturally cool into the ground state. And what's the second way? Some kind of gate. So we're going to do an operation, do a measurement, essentially, to project the system either into, or to project the system into some desired state. So like a H gate or some other operation. Could be an X gate. To project the system into our desired starting state. All right. What about long relevant decoherence times? They need to be much longer than the gate operation time. So decoherence times, they characterize the dynamics of a qubit in contact with the environment. And we can think about it in a very general way, at least for a logical qubit. So if we have our starting qubit state A0 plus B1, then the decoherence time is the characteristic time for our qubit to be transformed into a mixture. Rho equals a squared 0, 0 plus b squared 1, 1. And this is too simple, obviously, because we need to think about decoherence mechanisms in which the decay depends on the initial state of our qubit, and in which the amplitudes might change, and in which other quantum states of the qubit might play a role. You can think about the idea of leakage in quantum computing, for example. But this is kind of like, in general, what decoherence means. And it's really the principal mechanism for emergence of classical behavior in quantum systems. So we probably won't end up getting to the quantum eraser today, but I'll send you guys a way to build a quantum eraser at home. That'll be fun. And the thing you always want to think is if you're doing some complex quantum manipulation or thinking about a complex quantum system, and all of a sudden the system is behaving classically again, it's because of decoherence. There is kind of a rule of thumb that if the decoherence time is 10 to the 4th to 10 to the 5th times the clock time, so that's the time it takes to do an operation in your quantum computer. So the execution of an individual quantum gate, then error correction can be successful. So that's what people are trying to get to. All right, so let's think about our 3 measurements of decoherence. So T1, what's T1? Yeah, it's our excited state lifetime. Or our relaxation time from 1 to 0. So the probability of measuring a 0 in a T1 measurement is equal to 1 minus e to the minus t over T1. And that tells us that after, for example, 10 T1, then the probability of measuring a 0 is like e to the minus 10th, which is 4 nines. And so, as I mentioned last class, in NMR spectroscopy, we have this experiment that we run all the time called an inversion recovery experiment, and that tells us, that allows us to measure the T1 of our molecule of interest, and that gives us a way to set the delay times for our experiment so that we can get accurate integration. So we're going to set the delay to 5 times T1 so that we are confident our spins have relaxed back down to the ground state before we measure again. All right, so what about T2? Well, I guess let's start with T2 star. What's T2 star or T2? What are both of them? Yeah, they're the phase decoherence time, dephasing time. The simplest one to understand, I think, is T2 star, and that's measured via a Ramsey experiment. And if you guys recall, the Ramsey experiment is I take my 0, I apply a Hadamard gate, I wait a little bit of time, I apply another Hadamard gate, and then I measure, and I ideally get back 0. But once we move to the equator, we begin to drift around the xy plane. So you can think about this wait time as being replaced by a little rotation matrix that will give you information about how much you've drifted along the equator. Eventually, during that wait time, during the identity gate time, the quantum state's going to decay back to 0. So putting the final Hadamard gate in place moves you back to the equator, where the probability of measuring 0 is a half. So that's not great. So there's a related experiment, the T2 experiment, and that's our Hahn-Echo experiment that you saw in your quiz. And it's very similar, except that we're only going to wait half the time that we waited in the Ramsey experiment. And after we wait that half time, we are going to apply an X gate. Then we'll wait the rest of the time, and then we'll apply the last Hadamard gate, and then we'll measure. This is done so that you can cancel some of the phase drift. And so it's kind of referred to as a refocusing experiment. And it's why T2 star is always less than or equal to T2. And T2 is generally thought to be less than or equal to 2T1. And if you get a system where T2 is close to 2T1, then you say you made a really great qubit and you're very excited. So maybe I'll send this out to you guys in an email, but there's a really cool example that will allow you to see how to differentiate between T2 and T2 star. So if you kind of write down the noise for your experiment as being a really simple Hamiltonian where H equals the difference between the outer product of the one state, it's constant and it's unknown, and you apply that to both experiments, the Ramsey experiment and the Hahn-Echo experiment, you'll see that the probabilities that you measure in this very simple case are different, and that the probability of measuring 0 in the Hahn-Echo experiment is exactly 1, and the probability is less than 1 in the T2 star case. So I'll send that to you guys. Okay, so the last thing maybe we can touch on is our qubit-specific measurement capability. When DiVincenzo wrote this idea down, again, he was thinking about it very mathematically. He was thinking that if a qubit's density matrix is rho equals p outer product of 0 plus 1 minus p outer product of 1 plus alpha 0, 1 plus alpha bar 1, 0, then the measurement should give out a 0 with probability p and a 1 with probability 1 minus p independent of alpha and any other parameters of the system. And so you could use this to define what your 100% quantum efficiency in your measurement is. And then you can look at what happens if you have quantum efficiencies less than 100. So for example, if your quantum efficiency is 90%, then in the absence of any other imperfections, a computation with a single bit output, like one of those decision problems that we've talked about, will have a 90% reliability. And so if you need 97% reliability, then you could just achieve that by rerunning the calculation 3 times. And what would be even better than that is to copy the single output qubit into 3 by applying 2 C0 gates, for example, involving the output qubit and 2 other qubits, and set to 0 and measure those 3. So he was thinking about qubit-specific measurement capability in a very different way than what we were talking about earlier, where we were thinking, okay, if we want to measure fluorescence of our color center, we're going to use a fluorescence spectrometer. And so I think both are useful when we're thinking about developing our qubit systems. But I'll leave you there since it's 5:20.